This video is part 2 of a two-sequence set of videos covering section 3.5, non-homogeneous equations and undetermined coefficient. So in a previous video, we covered the first 4 pages of notes. In this video here, we're going to cover pages 5 through 7 of the notes to finish out the section. So first, let's just remind ourselves of the definitions here in section 3.5. We defined a non-homogeneous nth order linear equation with constant coefficients. Here I have some doodles from the last video. The fact that we have an f of x function on the right is indicative of the fact that this is a non-homogeneous DE. Had that right-hand side been equal to 0, call it homogeneous. And then we had theorem 5 from section 3.2 that said you can find the general solution of a non-homogeneous equation by adding together the complementary function y sub c, which is the solution of the homogeneous equation associated to the DE. And again, we learned how to find those in section 3.3. And then in conjunction with adding it to the particular solution of the non-homogeneous DE. So this section is working toward both determining a YP particular solution, but also finding that general solution by adding the two together. And so in the previous video, we introduced rule 1 here in the middle of the screen that said, look, as long as you don't have any duplication between the terms found by looking at your function and any of its derivatives, as well as when comparing it to the terms in the complementary function, then you're just going to a linear combination of all linearly independent such terms. And that's going to serve as your trial solution for YP. So we're going to turn our attention to page 5 here, scrolling down. And rule 2 tell us how to handle situations where we see duplication between the terms that we're identifying and the complementary function. So let's take a look here. Suppose that one or more of the terms in f of x or any of its derivatives satisfies the associated homogeneous equation. In other words, suppose that one or more of the terms is duplicated in the complementary function. Then take as a trial solution for YP a linear combination of all linearly independent such terms and their derivatives as in rule 1, and multiply through by the smallest power of x such that no term appears in YC. So let me highlight the end of that. This is what's new. Multiply through by the smallest power of x so that no such term appears in YC. All right, so the idea is by multiplying by a power of x, we're taking care of the duplication. This should seem familiar from section 3.3 when we had repeated real roots. Instead of just taking e to the rx root r, we had to incorporate there a c1 plus c2x plus c3x squared, et cetera, up until the number of duplication. So we're doing kind of a similar thing here by multiplying through by x. All right, and then determine the coefficients of this trial solution by substituting into the non-homogeneous equation. All right, so that's our main difference. Let's jump into an example to kind of see how we're going to handle these situations. So in problem 34, we want to solve the IVP. All right, just as we were doing in rule 1, we always want to start by considering the associated homogeneous DE and finding the complementary function. So I'm going to consider the associated homogeneous DE, which is y double prime plus y prime equals 0. And then from here, I can identify my characteristic equation, which is r squared plus 1 equals 0. And so I identify the roots of the characteristic equation to be plus or minus 1. As a result, I can set up my complementary function. I don't have a real portion of this imaginary root, so there's like an e to the 0 x if you want. I won't even write that. And then what I have here is c1 cosine x plus c2 sine x. All right, so we're going to put that in our pocket for later, and now we're going to move our attention to our f of x function. All right, So our f of x function is cosine, and already we can look here and we can see, yes, we definitely see duplication. Before I even compute the derivatives, I'm seeing duplication. So if I look at my derivatives of f of x, I first get negative sine x, negative cosine x, positive sine x, positive cosine x, and so on and so forth. So all we're seeing here is a shift in plus and minus, but we're always getting out sine and cosine. So we discussed in the previous video that we don't care about the coefficients in front because we're going to end up taking a linear combination. So no need to include those. The only real terms that we're dealing with here is cosine of x and sine of x. And so I'm just going to make a note here that we definitely have duplication when we refer back to our complementary function. We see both sine and cosine occurring, so we need to use rule 2 as opposed to rule 1. All right, so again, looking back at what's highlighted in yellow, we want to take the group of these terms, both trig functions, and we want to multiply through by the smallest power of x such that no term appears in the complementary function. So when I look at the complementary function, I only have two terms, c1 cosine x and c2 sine x. You'll notice that neither of those are being multiplied by x. So I can multiply through just by one x, and that's enough to avoid being duplicated in my complementary function. So I'm just going to make a note here, multiply by x to the first power. In other words, x. Just a single x will get me out of duplication. So I'm now ready to set up my particular function. And so that's going to be ax cosine x plus bx sine x. This is my, quote, intelligent guess as to what my particular function may be. Now, it may end up that maybe a or b is equal to 0, right? We're not sure. Now what we'd like to do is we'd like to utilize the original differential equation to solve for a and b. So here's where I like to remind you, what is AP, or excuse me, YP? YP is a solution to the non-homogeneous differential equation. So what that means is I should be able to plug it back into the original DE, and this should satisfy it. So when I look back up at the original DE, I have y and I have y double prime. I don't need y prime. But let me go ahead and compute y double prime so that I can plug it in. And so to get there, I need to compute the first derivative. So what I think I'll do, rather than doing the product rule twice, I'm going to factor an x out of here and write it as x times the quantity a cosine x plus b sine x. And I'm going to take the derivative of that expression. So using the product rule, this is going to be 1 times a cosine x plus b sine x. And then x times, taking the derivative of what's inside the parentheses, I get a negative a sine x plus b cosine x. All right, so here is my first derivative. Again, I don't particularly need the first derivative when I'm plugging things into the differential equation, but I need to compute it because I need to get to the second derivative. So let's go ahead and compute the second derivative. So I get a negative a sine x plus b cosine x. Now I'm going to apply the product rule. So the derivative of x is 1, so I get a negative a sine x plus b cosine x. Then rewriting the x and taking the derivative of that last set of parentheses, I get a negative a cosine x minus b sine x. So let's combine where we can. I can combine these two negative a signs to a negative 2a sign. And similarly, I have plus 2b cosine x. And then I'll just go ahead and distribute this x in back. So minus ax cosine x minus bx sine x. All right, so I need to use yp and yp double prime to plug this into the original DE. So let me just remind you, the original non-homogeneous DE said y double prime plus y equals cosine of x. All right, so we're going to plug this in using our yp and yp double prime. So I have negative 2a sine x plus 2b cosine x minus ax cosine x minus bx sine x. And now plugging in my original yp, I have plus ax cosine x plus bx sine x. And all of this needs to equal cosine x. All right, so luckily what we see is I have plus and minus ax cosine x, and same with the x sine x functions. So in the end here, I have a negative 2a sine x is on the left and a positive 2b cosine x is on the right. I have 0 sine x's on the left and 1 cosine x on the right. So I can now equate coefficients, and looking at this, I see that a equals 0 and b equals 1/2. All right, so what I have now is officially my particular function yp of x equals, okay, my a dropped out and I got my b to be a 1/2. So 1/2 x sine of x. All right, so this is officially my particular function. And at this point, I would like to solve the IVP by using the fact that my general solution is the sum of the complementary and the particular functions. All right, I'm running out of white space, so hopefully you budgeted a little bit more space than I did. All right, so what I'm going to do here is I'm going to say y of x is the complementary function plus the particular solution. Remember, the complementary function was c1 cosine x plus c2 sine x. And then we just determined the particular function, which is a 1/2 x sine x. Now, our first initial equation or initial condition was y of 0 equals 1. Let me go ahead and impose this into the solution that we have so far. That's going to give me c1 plus 0 plus 0. So I get c1 for free here. c1 equals 1. And then finally, I need to compute the first derivative to use the second initial condition. So the first derivative is going to be a negative c1 sine x plus c2 cosine x. And then product rule for the last term, 1/2 sine x plus 1/2 x cosine x. And moving here on to the next page, the second initial condition was that y prime of 0 equals -1, and that gives me 0 plus c2 plus 0 plus 0. So I conclude that c2 equals -1. So finally, I'm going to plug in these values into my y of x function for my final particular solution of the non-homogeneous DE. C1 was 1, so I get a cosine x. C2 was -1, so minus sine x. And then, of course, plus 1/2 x sine x. So this equation here in green is the solution to my non-homogeneous differential equation. All right, so very similar to what we were doing in the first half of the notes. The only difference here is recognizing that there's duplication between the terms and the complementary function, and we had to multiply through by an appropriate power of x to get out of that duplication. So I have an important remark here at the top of page 6 that says the following. In the event that f of x is the sum of two different types of functions, and when I say types, I'm referring to polynomials, and we're gonna include constants within the polynomial term, exponentials, and sine and cosine functions. Then when setting up the trial solution yp in rule 2, we need to separate those terms and choose the lowest power of x separately in each case. So what I mean by this is you may have duplication within your polynomials, but not in your trig functions. Or maybe your trig functions are duplicated and you only need to multiply by x, but your exponentials are even more duplicated and you need to multiply by x cubed. So I want you to keep those separate and handle duplication according to each individual type. All right, so let's take a look at these next two examples. I want you to set up yp, the particular function, but I don't want you to go through the process of determining the coefficients. So this is just seeing if you're able to identify the duplication and then identify the appropriate power of x to multiply by in order to set this up. All right, so let's consider the associated homogeneous DE so that we can find the complementary function. So the associated homogeneous DE would be the fifth derivative of y minus the third derivative of y equals 0. So in that case, my characteristic equation would be r to the fifth minus r cubed equals 0. If I factor, that's r cubed times r squared minus 1, or r cubed times r plus 1, r minus 1. So our roots here are 0 with a multiplicity 3, 1, and negative 1. So I can set up my complementary function according to those real and distinct and real and repeated roots. All right, so handle the 0 one. So we have e to the 0x times c1 plus c2x plus c3x squared. We had multiplicity 3, so we need 3 terms there. And now I have also c4 e to the x plus c5 e to the negative x. Now here you could drop the e to the 0x, that's just equal to 1. So if you just wanted to leave it as c1 plus c2x plus c3x squared, that's perfectly fine. So now I'm going to switch colors because I'm switching gears. Now I'm going to analyze the function f of x. So we have e to the x plus 2x squared minus 5. All right, let's list out our terms. So for the first set of terms, we see we have an exponential, e to the x. And furthermore, we know that all of its derivatives are also going to be e to the x. So those are the only exponential terms that we get. The next type of terms we're going to have are polynomials. The highest term that we see in f of x is an x squared. I'm ignoring the 2 because I don't need to worry about coefficients. Then if I took the derivative of the quadratic term, I would get a linear term. And then, of course, a constant term. So that 1 is also encompassing that negative 5 there in f of x. So I'm looking at each summand of f of x, looking at each of the derivatives that it's going to kick out, and I'm listing them all together. So we have exponentials and we have polynomials. So let's take a look at these. First, looking at the exponentials. The exponential is definitely being duplicated, as I've highlighted, but there's only one e to the x up in the complementary function. Multiply that e to the x by a single x, and that's enough so that it's no longer being duplicated in the complementary function. I don't, for example, see an x e to the x term in the complementary function, so I'm safe there. Now, we are going to look at these polynomials as a group, okay? Not individually, but as a group. We definitely see duplication. So let's color coordinate. We see actually all three of them being duplicated. All right, but it doesn't matter. Even if just one of them is being duplicated, that's enough. So the question is, what is the smallest value of x that we need to multiply by in order to get out of duplication? So if I try to multiply by a single x, that's going to take my polynomial terms and it's going to change them to x cubed, x squared, and x. That's not good enough because the x and the x squared would still be being duplicated. And same thing holds true if I multiply by x squared. I'm going to get an x to the fourth, an x cubed, and an x squared. The x to the fourth and the x cubed are good, but the x squared is still being duplicated. That's not good. So I need to go all the way up to x cubed in order to make sure that I'm no longer being duplicated. All right, and so at this point, I can go ahead and set up my intelligent guess for my particular solution. For that first one there, e to the x, I said I only needed to multiply by x, so that's an ax e to the x. And now for the rest of my terms, I need to multiply by x. So I get a bx to the fifth plus cx to the fourth plus dx cubed. And this right here is the setup for my particular solution. And I'm going to from it now that we do not need to solve for the coefficients. They just wanted us to set up the form for that particular solution. All right, so we'll do another example of this exact same type. Set up, but do not solve for the coefficients. So let's look at our associated homogeneous DE. We have the fourth derivative of y minus 2y double prime plus y equals 0. The associated characteristic equation is r to the fourth minus 2r squared plus 1. So this factors to r squared minus 1, r squared minus 1. And so we're getting two different types of roots, one with multiplicity 2 and -1 with multiplicity 2. So they're both being repeated. So in this case, we can set up our complementary function, keeping in mind the duplication of our real roots. So our complementary function is going to be c1 plus c2x e to the x plus c3 plus c4x e to the -x. All right, so here's our complementary function that we're going to consider when we're checking duplication. So now switching colors, moving back to the non-homogeneous DE. Let's take a look at our function. Our function is x squared cosine x. And we for sure want to include that term in our list of terms, namely x squared cosine x. But this function is a little bit more complicated. So let's list out some of the derivatives. All right, so the first derivative is going to be a 2x cosine x minus x squared sine x. Now, before we move on, let's just keep a running total of all of our terms. What do we have so far? We started with x squared cosine x. From the first derivative, we're now adding an x cosine x as well as a x squared sine x. All right, so I'm going to move on to the second derivative now to see if I get any additional new terms. So first, we'll work with this piece in orange. So we get a 2 cosine x minus 2x sine x. And now I'm going to move on to the next piece, minus a 2x sine x plus x squared cosine x. All right, so let's pause. That's the end of our second derivative. Have we added any new terms? This first term here is new. It's just single cosine. The second term is new. That's an x sine. Here I'm intentionally leaving off all those coefficients. Now I've already taken care of the x sine x, and I've also taken care of the x squared cosine x, so I don't need those. And by the way, it looks like I can combine a couple of terms here. So I am going to add this negative x, 2x sine x, and the negative 2x sine x. So this second derivative becomes a 2 cosine x minus 4x sine x and a minus x squared cosine x. All right, now let's think smarter, not harder. We started with x squared cosine x. So there's no need for me to pursue the derivative of that term any further because we're already looking at it, okay? We have not looked at the derivative of x sine x yet, so we can pursue that. And then also we have that single cosine, but we know what that cosine is going to kick out. It's going to give us a sine function. So I'm going to go ahead and add that into my terms. And then how about that x sine x? I'm going to get an x cosine x out, and I'm also going to get a sine x out. So I see both of those other terms in there. So at this point, I'm just going to say, I'm done. I don't need to look at any further derivatives because I'm just going to continue to repeat the terms that I have already listed. So when we take a look at all of our terms here, I have 1, 2, 3 cosine functions, and I have 1, 2, 3 sine functions. And when I look up top, hot diggity, I don't have any duplication. All of my terms up top were exponentials. And so in this case, I actually don't have any duplication, which means I don't need to worry about multiplying by any smallest power of x. But you can see why the book did not want you to work this one out and solve because it's going to have 6 unknowns. So let's go ahead and write out our YP. I'm going to scoot it over so I have room. So I'm just going to take a linear combination of all of these guys. I have ax squared cosine x plus bx cosine x plus cx squared sine x plus d cosine x plus e x sine x plus f sine x. So this whole function here is going to serve as our particular solution. And by the way, I just noticed I was being a little bit sloppy here. To be extra careful, you really should double check that your terms are linearly independent. Now, in the case of 30, that would take a ton of time to check linear independence because your Wronskian is going to be a 6 by 6. So in that case, I wouldn't ask you to do that on home or an exam, but certainly if you had a computer algebra system, that would make it quite a bit easier to check. In the case of 22, it's quite a bit easier just because your functions, even though it's a 4 by 4, your functions are going to be easy. So you could come up and you could check for linear independence here via a Wronskian. And because of the polynomials, you're going to have a lot of zeros in that Wronskian matrix. So I just wanted to make a note there that I am being kind of glib and skipping over that, but you should go and check through those things within reason. Problem 30 is not reasonable to go through that. All right. So we have one more example to round out the notes. Same exact setup here. We have a non-homogeneous DE. We want to set up the particular solution, but not solve for those coefficients. So I'm going to take a look at the associated homogeneous DE. So I have the fourth derivative of y plus 5y double prime plus 4y equals 0. Then its characteristic equation is r to the fourth plus 5r squared plus 4. All right, and so this is going to factor to r squared plus 1, r squared plus 4. And so we're getting complex roots, r equals plus or minus I and plus or minus 2I in this case. Let's set up the complementary function. So I have C1 cosine x plus C2 sine x plus C3 cosine 2x plus C4 sine 2x. Here is my complementary function. So now let's take a look at our f of x function. It is sine x plus 2 or plus cosine of 2x. And here I feel confident in listing out the terms without listing any of the derivatives. It just kind of depends on the problem. So the sine function is going to give me sine and cosine. And we know that those are just going to bounce back and forth between each other with potentially some negative signs popping out, but nothing more. And then we have our cosine 2x term. And if I take its derivative, granted, it's going to kick out a 2 from the chain rule, but it's just going to flip back and forth between sine 2x and cosine 2x. All right, so these are the only terms that I'm going to consider. So now when I compare those terms to that complementary function in green, I definitely am seeing duplication of, in fact, every single term. But even though every single term is up there, there are no x's being multiplied by those terms in the complementary function. So multiplying by a single x is going to do the trick. So I'm just going to note here duplication. And I just need to multiply by a single x. So that being said, I can set up, and actually, do we want to go through the computation of linear independence? Let's go ahead and do it. Let's just check that this is linearly independent. I don't know, this might be opening a can of worms, but let's go ahead and see, because it is going to be a 4 by 4. All right, so I'm going to write all of the functions across the first row. Then I'm going to write their first derivatives in the second row. And then another set of derivatives. And finally, the fourth row is going to be the third derivative. All right. So then just pick a row that you want to expand or a column that you want to expand along. I'm just going to do the first one. And so for the first term here, I have sine of x times the cofactor matrix and now we're going to move on to the next term. You would have minus cosine of x. And I think already we've bit off more than we can chew. I think this 4 by 4 is just going to be too nasty to do by hand. So just kind of leave the rest as an exercise. But in fact, I would recommend that you use something along the lines of Mathematica or MATLAB or some computer algebra system to carry this out, because this is just too taxing to do by hand. But this is how you would go about checking for linear independence. I am going to go ahead and make the safe assumption that these are linearly independent, else the book would not have asked us to solve this problem. And so assuming linear independence, we would set up our particular function. Again, I'm going to multiply everything through by an x. So I would get ax sine of x plus bx cosine x plus cx cosine 2x plus dx sine 2x. And this right here is the setup for my particular function, assuming that each of those four functions were linearly independent with respect to each other. All right, so this concludes our notes for section 3.5, solving the non-homogeneous DEs. And the concluding section in chapter 3 is going to be section 3.6, forced oscillations and resonance. And that is going to be kind of piggybacking off of our section 3.4 over mechanical vibrations and looking at applications of non-homogeneous differential equations. See you next time.